Okay, someone who needs no introduction. Ollie the foggiest.
Hello, it is me, Ollie the foggiest. I'm going to be talking a bit about vector databases and what they are, how they work, and a bit why they're so cool. And along the way, I'm going to talk about some sort of side concepts about embeddings, about RAG, which is retrieval augmented generation, which I'll talk a bit later, and similarity metrics and indexing. And don't worry if you're not familiar with some of these things. Hopefully, when we come out of this, we're all going to be experts. So all will be well. I think the very first thing we should cover is like, okay, what is a vector? Let's formalize this. It is a tuple of one or more scalars. So as in just a fixed size list of some length of a bunch of numerical values. It doesn't matter whether they're floats or integers, really. Please don't use integers for vectors in the context of a vector database. You can see at the bottom, here's a sample vector generated from an embedding model, which I'll talk about later. But you can see like it's a float. You could use integers, but like often vector databases are used with machine learning applications, and don't use integers for those. You could also store your scalars logged if they're very small. As you can see, these are not often very small. It depends on what actual like embedding model you're using, but this is not often necessary. So they're just a tuple of one or more scalars, a bunch of floats. And now what is a vector database? It is a database of vectors. We can all go home now. No, so it's a document database where every single document has a vector associated with it. And then that is sort of the core principle. It has all the same operations as a conventional document database. It has all the CRUD operations, create, read, update, delete. You can associate metadata with all of these documents. So typically these are little JSON blobs in NoSQL, schema lists, all that. I mean, you could create a sort of more SQL-centric version of it. Postgres has a vector database extension, which is obviously SQL. But the sort of conventional definition for a vector DB is, okay, it is a document database. But the main reason these exist, like the fundamental reason we have vector databases, is that we have this query operation where we can pass in a vector, so this n-dimensional tuple of floats, and we can pass in a parameter top k. And what the vector database will return is the top k most similar vectors in the database and the associated metadata with each document. So that concept of similarity is a bit obscure right now. I'll talk about that later. But for now, just think about it like, okay, these are semantically similar. I think I need to declare something up front. So I've mentioned machine learning a couple times. This is in secret. I've snuck a machine learning talk here. This is not a database talk. There's a lot of machine learning here. And so I'm sure you're all familiar with these definitions, but just to make sure everybody's on the same page, neural network, a machine learning algorithm, it emulates brain neurons. It has a bunch of layers of interconnected nodes, and it has edges between those nodes that are weighted. And those weights are trained with backpropagation to try and get these inputs and outputs to match some sort of cost function. And then a large language model is a super huge model that has been trained to produce and interpret natural language. And nobody's really sure how exactly these work. They use the new transformer architecture mainly. You know ChatGPT and Claude from helping with your supervision work primarily. And so one thing we need to clarify quickly is like, okay, we can pass in a vector, so a bunch of floats, and we can get close floats to it. How on earth is that useful, right? There's not many situations in real life where we have a bunch of floats that we want to find similar floats to. That's very abstract. What we really want to do is find like similar pieces of text or similar pieces of audio. And so what we need to do is create some sort of function that maps these vectors. Yeah, you can see my mouse, right? Yeah, you want to create some function that maps your actual input, like your text or your audio, to these vectors, and then get back some actually useful output. And so what we need to do is create this function. Like you could think of like, okay, I could use a hash function on the ASCII values of the text, and then that'll project it to the point in n-dimensional space, and then I'll get the closest things to that. But that's not very useful, right? When we do that query operation, it will get the closest vectors by that like arbitrary hash function, which is not good. We want it to be placed into space based on its semantic meaning. So when we query and get the closest things back, they're going to be semantically meaningful in context with the thing we're querying for. And so how do we do that? How on earth do we do that? We use embedding models. So here's like an n-dimensional space here at the bottom that has been projected into 3 dimensions, because we are not smart enough to think in multi-dimensions past that. At least I'm not. So we have this black box, this embedding model, that takes in some text. This could be audio, but for the purpose of this talk, we'll talk about text mainly. So we put in some text, live long and prosper, and this embedding model outputs, okay, the vector we want. Great, awesome. And when we put in something else, like may the force be with you, we get a similar vector. You can see in space these are quite close to each other. And that implies that, okay, these are semantically similar. But then we put in something completely different, like you will be exterminated. It's in a completely different area of the n-dimensional space. And so this embedding model, fundamentally, it can be anything. Like this could be any machine learning algorithm you could think of. I mean, transformers are used a lot by the big labs. I'll talk about this more in a second. But what matters here is the cost function is trying to minimize the distance, or the closeness, I should say, between actually semantically similar input items. And we want to maximize the distance between dissimilar items. So that is the cost function when we train this embedding model. So cool, okay. I mean, there's, as I mentioned a second ago, there's lots of different ways to do this. We could do a basic bag of words model, like from MLRD last year. You could use recurrent neural networks, transformers. I'm not going to go too into depth on these. I think that should be its own separate talk. But this is like a multivariable optimization function, right? Like, so there's a lot of things we want from this embedding model. Remember that this embedding model is run every single time we query the database. Since we need to turn our actual text query into a vector so that we can get the closest vectors, this needs to be fast, it needs to be cheap, because it's run on every single user query. So if it's slow and expensive, that's quite annoying. It's not very good. And so we also want to take context of tokens into account. So bag of words may be not the best option. We want to be able to say, okay, like if we put not, you will not be exterminated, that probably means something different to you'll be exterminated. And there's no sort of real way to do that without some degree of context, and that's what recurrent neural networks and transformers can do. But yeah, I'm going to skip over that, though. I'm just trying to give a whistle-stop tour before we talk about the interesting bits later. A couple real-world examples of these embedding models are the two big OpenAI ones. They launched like last year. Text embedding 3 small and text embedding 3 large. Don't let that fool you. Text embedding 3 small is gigantic. It's 1,536 dimensions, which is rather huge. And text embedding 3 large is double that as well. And the reason you want more dimensions is so you can get higher granularity, so that when you compare things in space, if you have more dimensions to look at, you have sort of more expression of semantic similarity that you can get across. But I mean, it's a lot more storage space, and it means your embedding model has to be like either a different architecture or needs more compute to train it, because you've got fundamentally bigger vectors going in and going out. So I mean, another key thing to note for later, remember this will come in helpful. OpenAI embeddings are normalized. So they sum up to 1. If we go back and look at this example I generated earlier, if you add them all together, it sums up to 1. And I do that for the actual similarity metric later for the calculation. Cool, okay. So we figured out a way to use machine learning to turn our things that we want to query for into points in n-dimensional space and then get similar things back. Cool, okay, let's prove to ourselves that this is useful. So if we can project a whole lot of things to these ND vectors, so images, network packets, whatever, music snippets and text, what this allows us to do is query for similar items. And there's a whole lot of use cases that that's good for. It's like checking for plagiarism, maybe the most clear example. If we put a ton of music into our vector database and embed that music into some sort of ND vector, and then we query with some sort of sample music MP3, we can get the things it's most similar to. And they might be too similar for comfort. Perhaps John does this with Superwork. I wouldn't be surprised. But we can also do classification tasks. So we can classify emails as spam. So we could upload a bunch of like sample spam emails into our vector database, embed them all, and then sort of test with our sample email to see how close it is to pre-existing spam emails. Sort of similar content moderation. If you're Roblox and you got a ton of kids, like millions of them, sending free-form text to each other, that's not ideal. We need some way to moderate that content. And typically you do this with just string matching. But anyone here who's played games will probably know that's easy to circumvent. You just change the letters to like numbers or whatever. It's fine. So it's a lot more powerful to actually do semantic similarity. And this is a really, really powerful tool for that. But perhaps most importantly, if you want to get rich, is building RAG chatbots. And RAG stands for Retrieval Augmented Generation. And this is a sort of big thing recently. I think it's best to show you with an example. Demo time. So let's just copy this over. If I go to normal, how do I? Cool, can you see that? If I go to normal ChatGPT, so this is ChatGPT 3.5 Turbo, and I've prepared a query. Give an example question from the Cambridge Computer Science Data Science course in Part 1B. If we wait for it to reply, let me zoom in a little bit. Here's an example question from the Cambridge Computer Science Data Science course. Consider a data set containing information about students, including their age, gender, grades, and I mean, I wish our questions were this easy. It's completely making this up. This is a hallucination in the parlance of the new LLM wave. So this is a hallucination. It's made up. What we can do is give ChatGPT access to a vector database. So we go to tripos.pro. Made this over the weekend, and we go to chat. We can talk to our helpful model and be like, okay, let's ask the exact same question. Give an example question from the Cambridge Computer Science Data Science course. So it's returned a bunch of questions from the data science course. It's given a helpful summary as well. Thank you, John. This question involves analyzing exam results using a linear model to assess the difficulty of exam questions. It covers concepts like linear independence, parametric resampling, confidence intervals. Awesome, let's verify that. So we can look at the actual question itself and read it. So exam paper, it's talking about exam questions. It's mentioned linear independence, yeah, parametric resampling. I think it's done a good job. So this is clearly a better answer than the one we got from standard GPT without any augmentation of retrieval augmentation. So that's all that means. So it's generation by an LLM that is augmented by retrieval from a vector database. And this query that it made, search the vector DB, is actually, it's actually made by the LLM itself. It comes up with, I say comes up with, it's very difficult to ascribe meaning to the actions of an LLM, but it has sort of learned to semantically come up with a query for a vector database that would be useful for itself. And it's interesting as well. I mean, this is a really cool interface. It goes really well hand in hand, LLMs and vector DBs, because LLMs work with semantic natural language, as do vector DBs, once you embed them. And I returned from the database 10 different questions by default. That's just how I hooked it up. And what it's displayed to us is 5, which implies it's doing a degree of intelligent filtering. I hope it's intelligent. And so it's a really fundamentally good user experience. I could have just made a search box, and it just literally searches the database and returns the answers to you, and then you manually check through them all. But doing it within a large language model means you get these summaries, get this intelligent filtering. Cool. Okay, let's go back to what we were saying before. Awesome. Okay, so we can do cool things. I think we've all proved that. This is a powerful tool. How on earth does this work? How does the query function work? And so to discuss this more, let's talk about first, okay, what is this similarity concept I glossed over earlier? Then I'll talk about how to make this fast. As I said earlier as well, I mean, this is the entire function of a vector database. We care deeply about this being quick. And then finally, what is the current state of vector DBs and what is the future? What are we moving towards? So cool. I think the sort of most intuitive similarity metric then would be, okay, so if we consider 2 vectors in ND space, they are similar if they're close together. Yes, that makes sense. That makes sense to me. So we can use Euclidean distance. Very, very simple. The problem is that, so this is used a lot, but often empirically, embedding models have better performance if they have some degree of directionality in them, as in there's an origin, and if one vector is out in this direction and one vector is out in that direction, it implies they're different in semantic meaning. And so that gives rise to this edge case here, where we have these 2 cases where they have the same distance between the vectors in each case. So it gives the same similarity metric. The Euclidean output is the same. But, I mean, based on empirical results, it's better performing if we take directionality into account. This one on the left should have higher similarity. But again, this similarity metric is baked into the embedding model as you train it. Your embedding model that you train, you choose a similarity metric up front. And so if you train your embedding model with Euclidean similarity, then it will result in good results. It's just like, it's better to take directionality into account, is what I'm trying to say. And so what we can do to take that into account is use something called cosine similarity. And so if we just normalize the dot product of the two vectors, we get the cosine of the angle between them, just from the definition of the dot product. V dot W equals magnitude of V times magnitude of W times cosine of theta. And so if we divide by the magnitude of both, we get cosine of theta. I've written a little bit up here as well, in that like, it's not just that empirically it performs better if you have directionality. Just getting rid of magnitude and distance altogether actually helps a lot, because magnitude normally acts as noise, which is kind of interesting. A lot of this is sort of like very loose. It's hard to interpret these models and why they work the way they do. And yeah, this depends massively on context and the embedding model that you're actually using. And again, I said this was helpful earlier. If our vectors are normalized, like OpenAI, then this is exactly equivalent to the dot product. Cosine similarity is identical, because magnitude of V and magnitude of W will just be 1. So cosine theta equals V dot W. And so V dot W is very easy to compute. You just sum up the components multiplied. Okay, cool. Okay, so I've talked a lot at you about some of like the technicalities of the theory behind it. How on earth do we actually implement this? How do we make our query function? We still haven't sorted that out yet. And I think the sort of easiest way to think about it is doing exhaustive search on the entire vector database. So you got your vector query, you go through every single item in your vector DB, you use your metric to get some sort of score. In the case of cosine theta, it's between -1 and 1. You sort them all, and then you take the top k. Great, okay, we got perfect accuracy. This is really slow though. If we have like millions of items, this is just not gonna work. So what we need to do to get to a higher performance is create an index. And indexes, in case you can't remember from databases last year, is they're pre-computed data structures, and they speed up our queries. And so for an example from like a document database, a more conventional one, they're pretty intuitive. You just create a new hash map with a different primary key, being whatever query, whatever field you're querying on, whatever column you're choosing to be the new primary. And so as an example, if we have course ID as the initial primary ID and primary key, and we have course name as a random column, it's very easy to look up, okay, get me the course with course ID 2. That is instant, because our main access pattern is like hashed on the course ID primary key. But what if we want to look up by course name? We'd have to do an entire scan of the entire table and check equality against every single course name until we get to the one we want. And so what we could do is create an index based on the course name column instead. And so we could, it's a little more complicated. We actually hash the course name values, but we instead make the course name the primary key, in which case it's a constant access time, and we get a pointer to the actual main table. So okay, I mean, this is pretty intuitive. We just shuffle around the columns a bit to make one of them the primary in our main hash map. But how on earth would we do that for looking up neighbors in n-dimensional space? That feels very different as an indexing problem. And it is. I mean, there's way cooler algorithms for this than there are for conventional indexing. And I'm going to talk about two today. I'm going to talk about IVF flat, and I'm going to talk about HNSW. But there are dozens and dozens and dozens of these. I've chosen these two because they're easy to think about and they're in memory. But I mean, there's GPU equivalents to them. You can sort of conceptualize that a lot of this stuff can be parallelized and make it quite fast. And there's actually a really, really cool on-disk algorithm called disk ANN. And Vimana, I think, or it's like the same algorithm. But that's for like billions and billions of data points distributed on like disk storage systems. That's pretty cool. But let's talk about IVF flat first. So the main sort of idea that we have to have here is that we can sort of create multiple layers of flat indexes. So if we, sorry, flat scans. So if we first off cluster our entire vector database into clusters based on closeness, you can choose any clustering algorithm you want here. It doesn't really matter. You decide up front how many clusters you want, and you just cluster everything. And then for each cluster, you compute a centroid, which is, a centroid is literally just like the mean value. It's some value that represents that cluster. It's like the center of that cluster. What you can then do is, so you divide vectors in clusters. Upon query, you get your query vector, and you find the closest centroid first, and that determines what cluster you then look into. So it's like a two-layer flat scan, if that makes sense. First off, you look at all the centroids, find the one that's closest, and then you look within that centroid's cluster to get like the the correct one in there. And so I've shown an example on the right. I mean, there's sort of an edge case where we're right on, edge case, it's right on the edge. Anyway, if you're on the edge and you get a centroid value that's like this one on the left here, then you're only gonna look inside that cluster, and you're only gonna get the nearest neighbors inside here. But what if the nearest neighbor is actually on this cluster over here? You're just not looking in it because that's not the centroid you picked. So what you do instead is you choose the top n closest clusters. You have some sort of n probe. You find adjacent centroids, more than one. And so you can see that there's a lot of like hyperparameters here, right? So we have to choose how many clusters we're actually making. We have to choose our n probe value, and none of this is done by us. Thank God it's done by the database itself. It's done computationally. And they figure out what is the best possible set. Like it's just an optimization function. But if we think a little harder about this, if we visualize all our vectors as points in space and they're similar to other points in space, isn't this kind of a graph? Isn't this sort of like a graph with edges being closeness, right? And if so, can we do some cool graph algorithm stuff? The answer is yes. Yes, we can. This was a leading question. There's a very cool algorithm I'm going to tell you about called HNSW. And so the intuition here is that, okay, we've got these 2 points in space. We got some source vector that we arbitrarily choose as our starting search point. We want to get to the closest nearest neighbor to this green one over here. And so intuitively, if we create a graph such that nearby neighbors, based on some arbitrary cutoff, have an edge between them, we can keep on scanning our nearest neighbors and find the one that's closest to the query vector and keep on iterating until we get to a point where we no longer have a closest neighbor. And so cool, we'd get there. And this is still worst case linear time, same as the flat scan algorithm. But the average case is significantly better. We're doing a lot of hops though, and we're looking at a lot of neighbors. So we can improve this. And so the improvement we really want to do is in that graph creation step. We don't have to just link adjacent nodes. We could also throw in a few long like highways. We could create some large like hops between very disparate points in our n-dimensional space. And that means that when we do this sort of step by step by step, we're going to hit a point where, oh, wow, there's this vector that takes us right there. And if we set up enough of these highways that cover enough of these regions in space, we'll get a much faster operation time. And so instead, it would look more like this. We start here, and okay, we take a highway, then there's a less small highway, and then the smallest, or more small highway, and then the smallest hop. And so this speeds up things a lot. So this is hierarchical navigable small worlds, HNSW. So this is actually what's used in almost every real-world vector DB. And so you construct a small world graph. So this is again from MLRD last year. A small world graph is just a graph that has a low distances and a high clustering coefficient. And what that means in normal person words is that most nodes aren't connected to each other, but most can reach each other via a small number of hops. So it's very easy to get from one side of the graph to the other side of the graph. But there aren't actually that many connections, which is really good for our use case because we don't want a lot of connections because that means that we're going to scan a bunch of them at every point in our iteration. So cool, we've got this algorithm now. But I mean, so we start at an entry point, scan neighbors for the closest to the query, keep on going until we hit something that's close enough. We can do better though. There is one final optimization that makes this logarithmic time instead of a bit more than logarithmic time, which is right now. And so what we can do is we can bring the hierarchical part of HNSW into this. When you construct this graph and you throw in these highways, you do this on separate layers. You construct different graphs. So instead of throwing everything into the same graph together, throwing these longer hops as well as all the mini hops, as well as all the medium hops, and layers, it doesn't matter how many layers, you instead put these on fundamentally different layers. So you start at the top layer, which is just the long highways. You start at some arbitrary entry point. You go to the closest one to your query vector. And then once you found the closest one, you go down a layer. And then you keep on going until you get the closest one. Then you go down another layer. And you keep on going until you hit the bottommost layer. And then you're in the little mini hops that are closest. And so what this means is that we don't have to scan every single neighbor, even the small neighbors. In this case, we would have been scanning every single small neighbor before we do the big hop. But in this case, we literally just restrict these search space to the large hops first, then the medium hops, then the small hops. Which means we get, super fast queries, really high accuracy, just really high memory costs as well, because now we've created all these graphs on top of our actual graph. And even the graph is not, like this is an index. This is in addition to our actual vector database itself. This is an index on top of it. So it's much higher memory costs. But it's very cool. And it's quite an intuitive algorithm as well, which is quite nice. So now to finish up, I'm just going to talk a bit about the real world. How do we actually do this? What does this look like in practice? There are so many vector databases because VCs love them. They make a ton of money. Here are some of the main ones. There's Pinecone. It's probably the most popular right now. That's what I use to make Tripos Pro. There's Milvus is like Pinecone, but significantly better, just with a worse developer experience. These are the guys who actually implemented disk ANN, which is the on-disk algorithm, which is super cool. Nobody else has done that yet. They're very powerful. Then you can also just use Postgres, which probably is the right choice for most people. You can just use the PG vector extension, and it performs just as well, if not better, than Pinecone, while also having your entire SQL database as well, which is pretty cool. I think that's everything I wanted to talk about. I wish you well in going out and creating your own ChatGPT wrappers. I hope this has given you the tools. Thank you very much.
Any questions in the room for Ollie? I'm just going to ask ChatGPT instead.
Is there any type of data that you shouldn't embed into a vector?
Well, that's a good question. I guess I mean, it's very much up to use case. I think if you create your own embedding function, you can create an embedding function for literally any data type, as long as you create some sort of, like, if you use a transformer, you create some sort of machine learning algorithm that has that cost function of like, okay, make sure they are semantically similar. I want to clarify as well, that semantic similarity, that's based on human labeling. So we need some sort of data set source here, and that's humans.
Any other questions?
Thank you, Ollie. I will be using TrackCode from this point forward. But with simple tasks like you mentioned the Roblox filtering text, and if you've got to have a labeled data set anyway, I think you know what the labeled data set is in this case. Is it not just simpler to craft a manual lexicon and go from there and hope that your data doesn't change too quickly over time? This will be very fast to compute when you need to. String matching is obviously very quick compared to querying a database, constructing it, storing it in memory, and Roblox's servers already don't work. It's a bad idea to make them worse.
Yeah, no, definitely. I cut out the bit of this talk about the future because I think it was running over. But the future of vector databases is actually hybrid search. So a lot of these vector DBs are moving towards a model where they have BM25 search, which is keyword search as well as having the vector search as a baseline. So it gives you that possibility of both having the keyword output, so it gives you some candidates for keyword matches and candidates for semantic matches. And then they have this intelligent BM25 model that like combines the two and sort of takes the intersection, chooses ones that are most relevant. And so what that means is you get the, that sort of indirectly answered your question, and that's also quite expensive to do. but it's moving towards the point where you delegate a lot of work to the keyword matching because it is actually more powerful. I mean, this example here, if I exit out of, like, Tripos Pro did not need to be a LLM. I mean, this question I asked, give an example of a question from the Cambridge Computer Science Data Science course. This could have been done with keyword matching. But what does matter is, like, okay, if I do something more semantic, like, oh, suggest me a question based on something I'm struggling with, might be something that this is better for semantic-wise.
Yeah, cool. I mean, assuming you've got like a massive field of semantics, if you've only got 5 important ideas per course, semantic things, then surely you could still use it. But I guess if you've got a lot, it's going to be a real pain, which is the natural language use case, right?
Yeah, I'd agree with that. I think it does massively depend on the data set.
Cool. Thank you.
What kind of thing are you passing into the vector database? Like, so here you say it says search the vector database. What is it searching?
Sure, I can show you. If we go to Pinecone, log in quickly, and we see the questions index here, you can see, okay, it's got 2017 questions in it. The parsing was awful. I hate the CST website. So much web scraping was done. But the actual items in this vector database are, so here's this metadata, which is this NoSQL JSON blob. it has this set of values up here. This is the vector, which is the text field here. So you can see this text field is like this straight up text from the question. It's passed into an embedding model, in this case, OpenAI, the text3 small model, which turns it into this set of vector scalars. And then it also has some associated metadata, like the tripos part and the year, question number, and the paper. And it has an ID. And so when we do this query, what I tell the LLM is I say, okay, you have a tool where you can pass in a piece of text as a query to a vector database, and I'll return some close documents. And what I do on the back end is like, okay, I turn that text query into a vector with the embedding model, and then I issue the request like, okay, actually search by a vector. And so like this is the exact use case. I'm querying the top 10 vectors, and it's returned a bunch of software engineering ones. But yeah, I mean, this is what it actually looks like.
Thank you.
Any other questions? Yes, Nils.
Hi, thank you for the talk. You mentioned that humans need to label this data to get similarity. Could you give examples as to how you'd label this data?
Sure, yeah, so one I think commonly way of doing this, a commonly done way of doing this is you compare different sample input texts, and you ask the human to say, okay, can you choose which two of these are the closest? I think there's also sort of ranking by closeness to some sort of main query problem. So it's like they give you one piece of text, and then they give you 5 options, and you rank them in order of similarity to the sample text. Is one way of doing it. I think a lot of this is also done through evaluation after you've trained. I'm not as confident on that bit though. I'd have to read more.
Thank you.
Any other questions in the house? Yeah. Tina was first.
Thanks for the talk. So if we wanted to perhaps create some sort of latent space between different modes of data, are there any other considerations that we'd have to think about if we want to create this vector space for multimodal?
Sure, I think the primary thing you need to worry about is like the number of dimensions. You also have to worry about like the embedding model that you're going to work with. You're going to have to worry about if you're interfacing with an LLM as well. Just the other tools in the ecosystem that you're interfacing with sort of determines a lot about the vector space you're trying to create. Does that answer your question?
Yeah, thank you.
Hi, thanks for the talk. Is there any meaning conveyed in the actual dimensions for your vectors, or is that arbitrary?
Sure. I mean, we can try and find out post hoc, but we don't know from the start. We can do mechanistic interpretability and try and figure out what these weights actually mean, and try and do some real world like psychology on these models. But it's not something we can just know by default.
Okay, thanks.
Any final questions tonight? Yeah.
Thank you for the talk. So you mentioned that the features are maybe not necessarily arbitrary, but the way in which they're designed is up to the ML algorithm and not human beings. Do you think that there's any possibility of looking into the feature space and abstracting concepts about the ideas that we're storing that we don't necessarily understand, like deeper notions of similarity between things in the database? Or is that not really worth looking into?
Yeah, I think that it's really, really cool, actually. I mean, like mechanistic interpretability is that field of like using like algorithms to try and find these circuits, they're called, in the models, and try and find these underlying mechanisms that understand concepts. And so like how on earth can large language models like multiply numbers together? That's non-trivial. That's not something that can be explained by text generation of just like generating the next token. There is some fundamental understanding there, but I mean that's still an open field. It seems pretty cool. I wish I knew more about it.
Thank you.
Okay, let's wrap up for this evening. So finally, round of applause for Ollie, our last speaker today.